Okay, so today's lesson on matrices. So first thing what I'd like you to do is have a go at this sort of question. Just pause the video and have a go at this two sets of question here. So the answer to part A, 6, 2, B, -2, 11, C, 8, -16, and then you got two sets of simultaneous equation. For part A, x is 7, y is 3, and for part B, x equals to -40/7 and y -23/7. So this sort of stuff you should already know. So matrices, you need to know how to find the dimensions of a matrix and add and subtract matrices of the same dimensions. A matrix is an array of numbers set out in a table of varying shapes and sizes. These sizes are described as the dimensions of a matrix. This is given by two numbers, n and m, and this would be written as n times n. Letter n represents the number of rows in the matrix, and m represents the number of columns. Matrices are usually denoted by a capital letter and is printed bold. So write down the dimensions of the following matrices. So I'll start off with the first one.
Wait, so should we copy out?
Okay, so straightforward. We've got this one, 2 rows and 2 columns. So we could write this as 2 by 2 matrix. Next one, we've got 1 row and we've got 3 columns. So this would be 1 by 3 matrix. Next one, we have 2 rows and 1 column. So it would be 2 by 1 matrix. And the last one, we have 3 rows and we have 2 columns. So this would be 3 by 2 matrix. You can add and subtract matrices. So if we look at this question here, so we've got 2 and -1, so that'll give you 1, -1 add 4, that'll give you 3, 0 add 5, that'll give you 5, and 3 add 3, that'll give you 6. So why don't you guys pause the video and have a look at this one. Okay, so if we look at the first one, so we've got 1, -5 on the first row, on the second row 3, 7, and on the third row 4 and -1. So you can use simple algebra when adding or subtracting matrices. So if we have matrix A, a matrix B, a matrix C, given that A plus B equal to C, we want to find the values of A, B, X and Y. So we substitute it in. Okay, so you simply equate the first one, so 2 plus B equal to 3, so B must be 1. 3 minus 1 equal to Y, so Y would equal to 2. 1 plus 2 equal to X, so X equals to 3. A plus 4 equals to 3, so A equal to -1. Okay, so for second part, half B, just multiplying each of these elements by half, so that should give you 3, 0 and -2. Okay, so here we're going to be looking at another two sets of matrix, A and B, or A, B and C, and this time we're told given that A plus 2B is equal to C, we want to find the elements of lowercase a, b, c. So first of all, A plus 2 equal to 6, so A is equal to 4. And the reason there's a 2 here because you're doubling B. So next one, A and then you got two lots of b, because you need to double the b. So 0 plus 2b is equal to 6, so b is equal to 3. So now you guys have a go at c. So now we do the same for c, and we get c is equal to 8. So the rule for multiplying matrices is what gives them the most useful properties. So adding and subtracting, so there's not much to it. The most application is to do with the product of the matrices. This rule is quite unnatural at first, and you should show large amount of working even if you feel you have fully understood the method. You multiply each row in the first matrix by each column in the second matrix. So it's row times column. The product will have the same number of rows as the first matrix and the same number of columns as the second. Okay, so if we have matrix A, B, and C, matrix A times B equal to C. So if the matrix of A is size n by m, then B must be of size m by k, and that will give you n by k. So these numbers must be the same for multiplication to be possible. These numbers will give you the dimension of the answer. So the rule for multiplying matrices, what gives them the most useful properties we said. So if we look at the value of A and B, so this matrix A, matrix B, that's 2 by 2, and that's 2 by 1 matrix. So these two are the same, so it will work. So let's go ahead and multiply this. So we do the row times by the column, and the same dimension. Two elements here, two elements that way. So 1 times minus 3 plus minus 2 times 2. On the next one, we'll go row times by column. So 3 times minus 3, add 4 times 2. So now we work this out, and that will give us minus 7, minus 1. So let's have a look at this one, matrix A and matrix B. We want to calculate AB and then BA. Well, that seems interesting, doesn't it? Because all this time, if you multiplied A with B, you would just assume it's same as B times A. But let's see if that's the case with matrices. So we've got 2 by 2 and another 2 by 2. So we should expect a 2 by 2 matrix at the end. So let's have a look at multiplying A and B. So you guys pause the video and have a go at this. So to do this, you look at the row. So in the row, first row, we have minus 1 and 0. And we need to multiply by the first column. So you will do minus 1 times 4. And then you will do 0 times that 0. Okay, so that will give us the first value that will go in here. And then we move on to looking at first row with the second column. So you do minus 1 times 1, and then 0 times minus 2. And then the next one, we move on to the second row times of our first column. So 2 times 4, 3 times 0. And finally, the second row with the second column. So 2 times 1 plus 3 times minus 2. So there are 4 elements. So we'll work out each one of these. Okay, so once we work this out, the first one with the minus 4, second one minus 1, 8, and minus 4. So what we need to do is calculate it the other way around. do B times A. Okay, so pause the video and multiply this to matrix. So Vitush, what did you get on this one? Okay, so same as before, row times column. So this is how you work out your first element, your second element, row times the second column. For your third element, first row times the second row times the first column, and finally second row times the second column. Now you work each one of these out. And you should get -2, 3, -4, -6.
Can we just try?
So what we notice here is A times B is not same as B times A. Okay, so multiplication using matrices is not commutative. So make a note of this, multiplication using matrices is not commutative. It could be in some rare cases, but most often it may not be commutative. So we've got matrix A and a matrix B and a matrix C. Determine whether each of the following can be evaluated, and if so, find the product. So AB, BC, CA, and BCA. So you guys have a go at this, pause the video. Alright, so let's look at A and B. So 1 by 3 and 1 by 2. So clearly these, the row and the column are not equal, so you can't do A, B. Let's look at B and C. So it's 2 by 2, sorry, 1 by 2 and 2 by 1. Here, you see the row and the column, it works. So you could multiply this one. So look at this, row times column. So 3 times 4, okay, and then -2 times 5. So that will give us 2. Okay, so now C times A. So we've got 2 by 1 and we've got 1 by 3. So the row and the column are the same size. So that will work. We're going to get a 2 by 3. So we do row times column for the first one. Second one, row times second column. And the third one, row times the third column. And now we go on to 5, the second row. Second row, first column. Second row, second column. Second row, third column. And you work this out, and it gives us the following. Okay, finally BCA. This can be done in any of the two ways. You could do BC first, then times by A, or you could do B times CA. It's really up to you. So remember, you cannot change the order. So for method 2, do not do CA and then do times B. It just doesn't work like that. You have to go in order. So BC, well, we worked that out earlier, is 2. So we go 1 by 1 times 1 by 3. Well, that would work because row and column matches. So we do row times by the column, and that gives us 2 minus 2 and 4. So there we have it. Let's look at the second method. We're doing B timesing with CA. So this is our CA. So we'll go 1 by 2 and we've got 2 by 3. Well, that will work because row and the column are the same size. So if you multiply the row with column on the first and the row in the second, row with the second column, and then the row with the third column, and we work this out, what do you know? We have the same result. So this is interesting. We just said earlier how A times B is not the same as B times A. But if you have B times CA or BC times A, it gives the same result. So that's an interesting property. Same answer. So here we've got two matrix A and B. Given that B times A is 0, we want to calculate A times B in terms of A. So first we should calculate B times A. So 1 by 2, 2 by 1. Well, that will work, and that will give us 1 by 1. So if we multiply this out, we get the following. Now we're told the B times A is equal to 0. So you could set this equal to 0. So 2A equal to B. Now calculate AB. So there's A, there's B. 2 by 1, 1 by 2. So we know that will work. So if we multiply these out, minus 1 times B, minus 1 times 2. Move on to the second row. A times B, and A times 2. So we get the following. We know from before that 2A is equal to B. So we can replace that. So we get the following. So why do we multiply matrices like this? Well, let's think about this set of equations. Here we have two pairs of equations. Write P and Q in terms of X and Y. Substitute the first equation and into the second, and you replace the U terms and the V terms. So it's just a bit of substitution. So multiplying out and simplifying. Okay, so you can see these are quite tedious. So mathematicians realized that for more complicated equations, they need a more efficient method. They wrote the set of equations as matrices and multiplied them using the method you have seen. So you could just write them like this. And I believe this was first introduced by an English mathematician in the 17th century. I think his name was Cayley. And at that time, people couldn't see any purpose of solving set of linear equations in this form. But in modern day, with computers, we'll see this is actually very important. Learning to do linear equations in matrices form. So if you put them as sets of equations, it makes the calculation a lot faster. And there we have it. So something that you would have done in a long way in the past, now you could put it in sets of matrices and work it out like this.